In this lecture, we will do a little bit more on the elementary matrices. First, we will talk about elementary matrices in R, and then we will look at the inverse of the elementary matrices. So this is R Studio. It works exactly the same as R, but it's a little bit easier to work with. R has a nice feature called packages, which allow developers to extend R by writing functions. Those functions are put into a package which you can download and install. In the bottom right window, you can look at the packages installed in your version of R. Once a package is installed, all you have to do is to click the checkbox to load the package, and all the features of the package will be available for you. If you want to install a new package, you just click Install Package. You can install packages from the comprehensive R archive network, or you can install from a local archive file. I have created a small package with some functions that are useful if you follow these lectures. So go ahead and download this file, install it, and then load the package by clicking. The first time that you install a package, you might be asked to create a personal library for the packages, which you should do. If you're looking for additional functionality, you can go to the archive network. You click packages. You have several thousand available packages to choose from. So once you've found one that you like, maybe you want to do some astronomy, for example, then just go ahead and download the binary depending on what computer you have, install it, and load it. Among the functions in the JLA package are functions to create elementary matrices. So there is the em1 function that creates a swap matrix, the em2 function that creates a scale matrix, and the em3 function that creates a pivot matrix. If you need to know how to use it, just type question mark followed by the function name. This you can do for all functions in R. And you will see a brief description of this matrix, how to use it, an example, and so on. For example, if I want to create a swap matrix, which is, let's say, 5 by 5, swapping rows 3 and 4, for example, I can just do this. This library also has a function called ranm, just to quickly create a matrix, n by n matrix with random element, which you can experiment on. For example, ranm 5, 5 creates a 5 by 5 matrix with just random elements. And if I pre-multiply by my elementary matrix 5, 3, 4, we know that this will give me a new matrix where row 3 and 4 of A have been swapped. Similarly, the scale matrix em2, let's say a 5 by 5, where I change the third diagonal element, and let's change it to -4, for example, and it looks like this. Pre-multiplying A by this matrix will multiply the entire third row of A by -4. And finally, the pivot matrix em3. Again, let's do 5 by 5. Let's change row 3, column 5, and let's make it into -1, for example. And that's your pivot matrix. Pre-multiplying A by this matrix will subtract the fifth row from the third. Here's another example, which will turn out to be an important example when we look at how to invert matrices and solve systems of equations. This is just an arbitrary 4 by 4 matrix. Let's say that I want to find an elementary matrix such that when I do E times A, I want the result to be very similar to A, but with the following change. I want this product to have, instead of this 2, I want that to be 0. No point right now asking why we would like that. That will become clear later. Also, I don't want any changes in these 3 rows, but I'm willing to accept that these numbers change. So that's my goal. Find an elementary matrix E such that the product has a 0 at position 2, 1, and only the second row is altered. The hint to what E must be lies in multiplying the first row of A by -1/2. If I do that, the first row of A becomes -2, 0, -2, and 0. The second row is 2, 7, 0, 6. That means that if I add -1/2 times the first row to the second row, I will get a 0, 7, -2, and 6. The important number being this 0 here. So what we see is that if I can add -1/2 times the first row of A to the second row of A, the second row of A will have a 0 in column 1. But there is an elementary matrix which does precisely this. It's the pivot matrix. It must be 4 by 4 so that multiplication is defined. If I only want to change the second row of A, the pivot scalar must go into the second row of E. If I want to add a multiple of the first row of A, the constant must go into column 1 of the pivot matrix. And the constant that I need to use is precisely -1/2, as we found up here. And so this is the elementary matrix, which will produce a matrix with a 0 in position 2, 1. Check that this actually works. If I do the multiplication, we see that A1 actually does have precisely a 0 in position 2, 1. Similarly, if I want this 9 to go into a 0, I again pre-multiply with the pivot matrix 4 by 4. In this case, I want to change the third row such that this goes into 0. I use a multiple of the first row, and in this case, the multiple I need to use is 9 by 4. If I multiply the first row by -9 by 4, the first element will become precisely -9. Adding that to the third row will make 3, 1 into 0. Like this. And we see that we have now gotten this one to be 0 as well. And you can play around with this yourself, making this guy into 0 also. Next, let's take a look at the inverse of the elementary matrices. They are all square, so it's possible that they are invertible, and it turns out that every elementary matrix is actually invertible. Let's begin by looking at the swap matrix. So here I've swapped rows 2 and 4 of I5. That's this. If you do the inverse of this, you see the pattern. You see that this becomes exactly the same. And that's not a coincidence. The inverse of any swap matrix is the matrix itself. So we have this result. This is not hard to understand. Remember that B is the inverse of A if A times B is the identity matrix. What we are saying is that the inverse of the swap matrix is the matrix itself. So to prove that, I need to show that when I do this multiplication, 1 I, j with itself, I must get I. This is what I need to show. If I can show this, then for sure this is the inverse of that. But this is fairly obvious because this second matrix is the swap matrix where I've swapped rows I and j. If I pre-multiply by a swap matrix, swapping rows I and j, I know that the result will be to swap rows I and j of the second matrix. That is, the effect of pre-multiplying by this swap matrix on a swap matrix is to revert it back to the identity matrix. And this is why the swap matrix is the inverse of itself. It's actually not a bad practice to try to do this for a simple case. Let's say I swap rows 2 and 3 of I3. So I have this. Try to do this matrix multiplication and convince yourself that you do get the I3. Let's take a look at the scale matrix and see what the inverse of that is. Taking the inverse, you see the result. What happens is that the diagonal element, which is not 1, gets inverted in the inverse. This will be true for every scale matrix, and we have this result. The inverse of the scale matrix is the same scale matrix, but the scalar goes from alpha to 1 over alpha. Again, this is fairly trivial to see. To prove it, I need to prove that this first E matrix multiplied by the second E matrix is equal to the identity matrix. But it must be, because if I pre-multiply the second matrix with the first, that will multiply the entire row I of the second by alpha. And if you multiply 1 over alpha by alpha, you get 1. So the product is indeed the identity matrix. Again, a good idea to try this out with a simple, say, 3 by 3 case. Finally, the pivot matrix. Here's an example of a pivot matrix. The off diagonal 2, 4 is minus 3. If I invert the pivot matrix, you see exactly what happens. The pivot element changes sign. And this always happens for pivot matrices. And we have the following result for the pivot matrix. So if I have a pivot matrix with an alpha in row I, column j, the inverse of this pivot matrix will have a minus alpha in row I, j. Again, not too hard to prove this. All we have to prove is that the product of these two is the identity matrix. And that follows because when I do A times B, the rules of pre-multiplying by a pivot matrix tells us that I should do minus 3 times the fourth row. That is minus 3 times this one. That will give me 0, 0, 0, minus 3. Then I should add that to the second row. If I add this to the second row becomes 0, 1, 0, 0. And it's only the second row that's affected. All the other rows are consistent with the identity matrix, and we see that the product is indeed the identity matrix. Even if you don't remember precisely the inverse of the elementary matrices, what you should remember is the following. All the elementary matrices are invertible, and the inverse of an elementary matrix is always an elementary matrix of the same type. We see that both of the matrices in the first bullet are swap matrices, both of them in the second are scale matrices, and both of them in the third are pivot matrices.